Okay, to start off section 3.6, we're going to learn a really simple concept with mass percents that actually gets quite challenging when it's out of context. It's a really simple skill, but sometimes you don't think to use it. We just don't think that way in science. You're really used to formulas instead of concepts. But it's just a really simple idea. It says calculate the mass percent of each element in glucose. So C6H12O6, first thing we want here is the molar mass. It's really easy to get. Add all those up, 180.18 grams per mole. Now if we want the percent of each element in that mass, percentages are the same. There is a fancy formula for this in the book. Do not look it up. This is just your thinking skills. How do you get a percent? Well, there's a part and there's a total. If we want a mass percent, we want the part of the mass and the total mass. So carbon is, the mass is 12.01, and there are 6 of them. So carbon has a mass of, you total that up, you get 72. Over the total is 180.18. That is the total carbons divided by the total mass, part to whole, times 100%. And the mass percent, 72 out of 180, the percentage of the carbon mass is about 39.99% of that mass. That 180 comes from the carbons. Hydrogens, we know it's going to be small because they each weigh 1. So all 12 hydrogens is 1.01 times 12 over 180.18. times 100%. You do need to write that 100% there. You can lose points for that on the AP test. You cannot divide 12.12 over 180 and get a percentage. So 6.727% hydrogen. Oxygen then, there's 2 ways you could do this. If you're confident with the rest of your numbers, you can add up the 39.9, the 6.72, subtract from 100. But you might as well go to the source just to double check your work. We have 16 as the mass of oxygen. We have 6 oxygens over 180.18. And we get the oxygen has the highest mass percentage of any element. The useful part of this is that those mass percents are constant. This is sugar, C6H12O6. It does not matter if you have 1 grain of sugar or a couple gallons of sugar. The mass percents are constant. There's always a 6 to 12 to 6 ratio. The molar masses will always be in this ratio. It'll always be 40% carbon, 6% hydrogen, 53% oxygen. You can use this information in a variety of contexts to solve all sorts of problems. This is a rather direct problem where it says calculate the mass percent, where you know what to do. But just the idea that every sugar molecule has these mass percents in it can be a useful skill in another context. Here's another one. It's a little bit backwards. We learned about hydrates in one of our labs. A hydrate containing 3 water molecules is found to be 13.6% water by mass. A hydrate is an ionic salt, and it's just some unknown ionic compound, and they're saying that this one has 3 water molecules in it. So times 3 H2Os, and we add those 3 H2Os to the molar mass. Now we know that that hydrate is 13.6% water. So 3 waters, water molar mass is 18.02. The water portion of this is 54.06 grams. That's how much oxygen we have, grams per mole, if we dealt with a mole of that. So we can get the mass of those 3 water molecules. Now we know, just simple algebra here, we can go backwards. 54.06 is going to be equal to 13.6% of the total molar mass. And I can't spell. So again, you don't have to think in fancy formulas, you just have to think a little bit. You know how percentages work? They're talking about mass percents in this case. Sometimes we'll talk about mole percents. Sometimes we'll do it in fractions. We're going to do various sorts of things throughout the year. You don't need to memorize the formulas. Percent yield, it's like how much you get in a lab. It's just a little bit of logic. 13% of the total is going to give us 3 water molecules. Okay, but this one kind of, you had to know what hydrate meant to be able to solve that. Here when we start working with empirical and molecular formulas, we have to know the definitions that an empirical formula is the lowest whole number ratio of an element based on its analysis here. So it's mass percent. So we've got 87% of the mass is from nitrogen for rocket fuel and 12% is hydrogen. With percentages and mass percents, it does not matter how big the sample is. 87% is always going to be nitrogen. You can pick any sample size that you want. It's convenient if you have percentages to just work in grams. Let's just say 87.4 grams of nitrogen. And if I have 12.6% hydrogen, let's say I have 12.6 grams hydrogen. Now I have those percentages in the correct ratio, nitrogen to hydrogen. And if I want a mole ratio out of those, which is all an empirical formula is, I just need to figure out how many moles I have. Since we have an unknown element, it's important to note that we are not talking about the diatomic version of these. We are just talking about the whatever molecule they're in. This one is rocket fuel. It will not be the diatomic version of nitrogen and hydrogen because we're trying to figure out what that ratio is. So we're just going to use atom by atom. It's the only time we do this. Normally if we say nitrogen we mean N2, but this is an unknown molecule. It is not N2 and H2. It's an unknown rocket fuel. So here we've got 6.238 moles of nitrogen, and we have 12.475 moles of hydrogen. Now this one looks pretty obvious because it's simple. They won't always be, but we need to make this into a whole number ratio. To get a simplified ratio that are whole numbers, we have to compare these two. We kind of casually say divide them all by the smallest one. That will give you whole number, or at least larger than one, numbers larger than 1. And we can see that this comes out to for every 1 nitrogen we have 2 hydrogens. Which 6 to 12, we could kind of see that anyway. It's a 1 to 2 ratio. They won't always be that visual, but this one is. So it's a simple 1 to 2 ratio. My empirical formula is NH2. Now the molecular formula is a little different. There's my empirical. We're given this other piece of information that says it has the actual molecule has a molar mass of 32. So we can compare that to this and see what happens. So this is my empirical. This is one answer for the empirical. This has a molar mass, though, of 16.03 grams per mole, which is not the 32.05. Again, this is a simple one to see. The actual molar mass is 32. My empirical is 16. My molecule is going to be 2 times bigger. It has to be in this 1 to 2 ratio, because that's what my empirical formula data showed, but my molecular formula is double, N2H4, and that will match the 32.05 and meet that criteria for the molar mass of my molecular formula. So the empirical is the reduced version, the molecular is the actual one, and to go between them you'd have to know this molar mass here. For a problem like this, to go up from the empirical to the molecular, you have to compare their molar mass ratios. A much longer problem, but you can do this with all 5 of these: carbon, hydrogen, oxygen, phosphorus, and fluorine. If we turned all of those into grams and we just said, okay, 39.10 grams of carbon, grams of hydrogen, grams of oxygen, and we have all of these grams. Convert all of these to moles, we can get a mole ratio. So once we do that, there's all the work. If we convert all those grams to moles for each one of those elements, we will see their mole ratios. Now this is a much more difficult problem to just see with your eye, and there's 5 of them, but the idea is the same. We want a whole number ratio. We're going to divide them all by the smallest number to give us whole numbers. It's this 0.0542, 0.0543, they're about the same. If we divide everything by that, 0.542, this one is 0.542. I'm sure this is getting tight on the screen. We go through all that math and we will see we have 6 carbons, that's a whole number. We're going to get 14 hydrogens, 3 oxygens, 1 phosphorus, and 1 fluorine. Okay, so that's enough to give us our our empirical formula. We say C6H14OPF. We get the molar mass of that, we add it all up, and it's 184.17 grams per mole. And we see that it matches the known molar mass is 184.1. This empirical formula is both the empirical formula and the molecular formula, which is really common because it's not reducible. Okay, so the most complicated application of this is by far the combustion data used to determine an empirical and molecular formula. Now we haven't looked too much at balanced equations yet, or really what combustion necessarily is. Right now there's some assumptions we need to solve this problem. You need to understand what combustion is. Combustion is where we have some sort of fuel, which is a hydrocarbon. Well, we add oxygen to it, and if it's just carbon and hydrogen, maybe some oxygen in the fuel, we get carbon dioxide and water. Now there are some other elements on Science Geek that can come up. You might get like nitrogen dioxide if there's nitrogen in it. There's more than one way to do this, but the process is still the same. Conservation of mass and mass percents to figure out how much of each element are in the sample so that we can get an empirical formula. In this case, our fuel, they say there's only carbon, hydrogen, and oxygen. We don't know how much those are, so we can't really make a mole ratio out of those. But in looking at this combustion balanced equation, we can see in conservation of mass that all of this carbon turns into carbon dioxide. All of the hydrogen turns into water. And oxygen is in all 4 species. So we're going to do the oxygen last for sure, but we can keep track of the rest of this over here. We're going to use this 1.603 grams of carbon dioxide in order to find out how much carbon is in that sample. And then we've got 0.2810 grams of water, and that'll tell us how much hydrogen is in that sample. And if all of this carbon turned into carbon dioxide, if I know what percent of this is carbon, it tells me how much is in my formula to start with. So we can use mass percents because the law of definite proportions says that all carbon dioxide samples have the same makeup, the same percentages. So let's just assume we have 1 mole, and we know that there are, I'll start over here, we've got CO2. There are 12.01 grams of carbon in every CO2 molecule, which weighs 44.01 grams. So that gives me a mass percent of CO2 that is, if we do times 100, it's 27.3 0.23%. So 27% of the carbon dioxide sample is carbon. Well, that means 27% of 1.603 is carbon. So that gives me 1.603 grams of CO2. And we know that 27%, so 0.2723 is carbon. That's going to give us 0.4365 grams of carbon. Okay, and that originally came from our unknown sample. The water is going to be the same thing. Now there's two hydrogens here because that's what we're after. So there are 2.02 grams of hydrogen in every 18.02 grams of water. All right, times 100%. That gives us a percentage of 11.21% is hydrogen. So 0.1121, that's 11%, times my original 0.281 sample. That's going to give me 0.0315 grams of hydrogen. Okay, so there's the first part of the sample, understanding what combustion is and keeping track of the mass percents of each substance and understanding conservation of mass, how they all apply. The second part of this is taking those answers and making an empirical formula out of them. Our fuel, if you remember, was carbon, hydrogen, and oxygen. The total sample of the fuel was 0.6349 grams. We know that we just solved for 0.4365 grams of carbon, and there were 0.0315 grams of hydrogen. That means the remainder there has to be the oxygen. So there's no mass percents we can do for the oxygen. We simply subtract all of these. The total was 0.6, the carbon was 0.4, the hydrogen was 0.03. So the remainder there is going to be the oxygen, which is 0.1669. And that's going to give us all the numbers we need to make an empirical formula. All right, so we're going to take those guys, and we just need now we need a mole ratio from them. So let's start out here. We have 0.4365 grams of carbon. We're going to convert that to moles. We have 0.0315 grams of hydrogen. And we're going to convert that to moles. And we have 0.1669 grams of oxygen. So we're going to convert that to moles as well. 16 grams of oxygen for 1 mole of oxygen. That is going to give us, let's see, carbon is 0.0363. The hydrogen is 0.03119. And the oxygen is 0.0104. Oxygen is the smallest value there, so we're going to divide by the smallest one to get all of our mole ratios to be whole numbers. And we get 3.5 carbons, so that's not a whole number yet. We'll deal with that in a minute. We get 3 hydrogens and 1 oxygen. So this isn't quite done yet. 3.5, you can't have a subscript of halves. So we need to keep them in this proportion, but we need them to all be whole numbers. We haven't had to deal with this in other problems yet, but we can simply double all of these values as the last step. Keep them in a 3.5 to 3 to 1 proportion, but how do you get them to be a whole number? This decimal is the only one that's not. If we double that, we get whole numbers. We get 7, a 7 to 6 to 2 ratio. So our empirical formula, when we move that out of the way here, is C7H6O2. All right. There is our mole ratio. We kept track at the beginning of the mass percents of the carbon and hydrogen that turned into different molecules to kind of backtrack them through the experiment. And then we found out the mole ratio, just like we'd done for any other empirical formula problem, of elements to figure out what the unknown substance was. So just by burning it, we're able to reverse engineer what the actual formula was of the substance that we burned.